guys and gals. Let's start. So we're trying to do the Gaussian quadrature, and we've been able to compute the Legendre polynomials, compute their derivatives, compute their roots, compute the weights of the quadrature. By the way, it seems like these formulas that we've used are arbitrary, but it's possible to derive them. And there are other cases that might be interesting. So if the function you want to say it's a polynomial, but it's close to a polynomial, it looks a bit like a polynomial, maybe with some extra stuff, then you can use the Gaussian quadrature. If you have a function that's basically perturbation on a exponentially decaying function, there's something called the Gauss-Laguerre quadrature, which just uses other polynomials, and there's also, if you want the function to be a bell curve like a Gaussian, but perturbations on that, you can use Gauss-Hermite quadrature, and those I'm going to take a wild guess and say that the Gauss-Laguerre quadrature use Laguerre polynomial, Gauss-Hermite use Hermite polynomials, but maybe if you're interested you should look that up, because I'm not sure. So now we have to put it together, okay? And we're going to have a formula for the integral of a function, but when you do an integral you need to specify what the boundaries of integrations are. So in the case of the Gaussian quadrature, if you use the just plain old Legendre polynomials, it's good for integrating between -1 and +1, but that is not a true restriction on the kinds of integrals you can do, because you can always do a change of variables in order to integrate a different function between -1 and +1. It's going to give you the same value as the function you wanted between A and B. So let's just write down a little bit. So integrate from A to B function f. I have to write it as integrate from -1 to +1 of function g. We prefer writing it as f of x and g of x, or g of y or something. How do you do that? So when x goes from A to B, y goes from minus 1 to 1, and it's y equals to mx plus b plus k. Okay. So it's a linear transformation that we want. How can we do that? Okay, well, you can actually just plug the values in. So minus 1 equals m times a plus k, and plus 1 equals m times b plus k. And we need to find m and k. So if you subtract the two equations, you get so minus 2 equals m a minus b, and then the k's cancel. So from this formula, from this equation, we get that m equals to minus 2 over a minus b, which is just 2 over b minus a. And you can plug that in the second equation to get 1 equals to 2 over b minus a times a plus k. So k equals to 1 minus 2 over b minus a times a. Okay. You can actually simplify that if you want by putting everything on the same denominator. So b minus a over b minus a minus 2a over b minus a k equals to that. That's the idea. And then b minus a minus 2a is b minus 3a over b minus a. Okay, so final equation, y equals to two over b minus a times x plus b minus 3a over b minus a. Okay, we can rewrite that. 2x plus b minus 3a over b minus a. Right, and then dy over dx, right, the derivative will be just 2 over b minus a. So dy equals 2 over b minus a times dx, and then so when we integrate dx, right? It's going to be integrate from -1 to +1 g of y times b minus a over 2 times dx. Right? Hopefully I got that right. So dy. And so that's the function we're going to integrate. You give me f, and then I compute this weird function. That's the one I'm going to use. Okay, so weights of quadrature. And quite info. Is that a good idea? My idea is that if you so you want to say integrate between a and b f, right? Integrate between a and b in the function f. Then you'd want to have a mechanism for not repeating the work every time that you're integrating. So the mechanism would be to pass a pointer, or the address if you like,